Physical and mechanical properties of dental materials. To predict how a material will react under oral conditions, it is necessary to have an understanding of its physical properties. This chapter discusses how those properties are achieved, how they influence the clinician's choice of a material, and how and when properties can be manipulated. Both physical and mechanical properties must be considered when choosing the best restorative dental material. Physical properties are those properties of materials that can be measured and observed without having to change the composition of the material, and they help describe it. Physical properties include properties such as color, thermal conductivity, and solubility. Mechanical properties are properties that define the material's ability to perform in the oral environment and resist stresses and strains. Mechanical properties are considered a subset of physical properties and include properties such as elasticity, ductility, durability, and ultimate strength. Electrochemical properties are seen in the reactions of materials as they set or their reactions to corrosive elements in the oral cavity environment and their chemical stability and durability in the mouth. To begin a discussion of the properties of dental materials, it is important to begin with a review of the physical structure of matter. Physical structure. Atoms. Atoms are the basic building blocks of matter. They are composed of particles called neutrons, protons, and electrons. Protons have positive electrical charges, electrons have negative charges, and neutrons have no electrical charges. Neutrons and protons, being heavier than electrons, form the nucleus in the center of the atom. Electrons are found in orbits, also called shells, around the nucleus. It is the outermost orbit in which electrons, called valence electrons, will interact with other atoms. The numbers and configuration of electrons in their orbits affect how reactive they are with their other atoms. Some atoms have space within their outer orbits, while other atoms have extra electrons in their outer orbits. Atoms attempt to form the most stable configurations possible by filling their outermost orbits with electrons when bonding with their other atoms. To do this, they will transfer or share electrons, and that leads us to types of bonds. There are two categories of bonds that are formed between two atoms. Strong bonds are called primary bonds, and weaker bonds are called secondary bonds. Primary bonds are the strongest bonds that hold atoms together because they involve the transferring or sharing of electrons. The three types of primary bonds are covalent bonds, ionic bonds, and metallic bonds. Covalent bonds represent a type of bond that occurs when two nonmetal atoms share electrons in their outer shells, creating full shells for both. Many covalent bonds form gases, hydrogen, molecule H2, or materials with low melting points. Covalent bonds occurring in a network configuration are very strong. Diamond is a good example of a strong network covalent bond. It is hard and has a high melting point. Some materials are made up of chains of covalent bonds. Polymers used in plastic and rubber are good examples of long chains of covalently bonded atoms. Ionic bonds. When atoms gain or lose electrons, they become electrically charged and are called ions. Positively charged ions are called cations, and negatively charged ions are called anions. Ions that have opposite charges have electrostatic attractions for each other. When they combine, one atom gives out electrons from its outer shell and the other atom gains electrons. The energy that holds these atoms together to form a molecule is called ionic bonding. Salt and sodium chloride is an example of ionic bonding. Materials bonded in this way, such as ceramics, are usually brittle when they are pulled or bent and are poor electrical conductors. Ionic bonding can also be seen in gypsum products and phosphate-based cements. Metallic bonds. When atoms join to form metals, they bond in an entirely different manner than the covalent or ionic bonding, but they still attempt to form stable outer or orbits. Multiple atoms in a lattice arrangement share a large pool of valence electrons that move throughout the material. This sea of electrons passing among the atoms produces what is called metallic bonding. Imagine filling a bucket with marbles and then adding water. The marbles are arranged in a structured manner and the water fills the spaces between them. The water is like the sea of electrons that is shared by the metal atoms represented here as marbles. It is this type of bonding with freely flowing electrons that is responsible for many of the physical properties seen with metals such as their strength or ability to conduct heat and electricity to be formed into shapes such as coins or jewelry, malleable or stretched into wires, ductile, like those used in orthodontics. Combination of primary bonds. Many materials contain more than one type of primary bond. Secondary bonds. Secondary bonds, broadly called van der Waals forces, are very different than primary bonds. Unlike primary bonds, no transferring or sharing of electrons occurs. Secondary bonds are forces found between molecules in the same material, attractions between water molecules rather than forces that bond atoms together in a molecule, such as covalent bonding of hydrogen and oxygen atoms to form a water molecule. The secondary bonds are created by various types of electric dipoles. A dipole is created when electrons are unequally shared between atoms within a molecule, forming positive and negative charge centers at each of the molecule, causing an electrical imbalance. Secondary bonds are much weaker than primary bonds, and 3 examples of secondary bonds include hydrogen bonds, permanent dipoles, and temporary dipoles. Hydrogen bonds. Hydrogen bonds are dipole-dipole interactions. They exist in molecules where electrons are not shared equally and thus have electrical poles. In the case of water, hydrogen is attracted to the larger oxygen atom. Although electrons are shared between the hydrogen and oxygen atoms, these electrons are unbalanced, spending more time around the oxygen atom. This causes a partially negative charge on the oxygen side of the molecule and a partial positive charge on the hydrogen side, setting up 2 opposite electromagnetic poles called dipole. They act like a magnet, attracting opposite charges. These bonds are responsible for many of the properties such as solvent properties. Cohesion sticks to itself, and adhesion sticks to other materials, and density. Hydrogen bonds are the strongest of the secondary bonds, but still much weaker than the primary bonds. Permanent dipoles. Permanent dipoles in a molecule have a positive and negative charge centers that do not fluctuate, and the molecule must consist of atoms from different elements. A permanent dipole is formed when one atom in the molecule has a stronger electron attraction than another atom, and therefore becomes more negative in its charge. Then the other atom becomes more positive in its charge. This electrical imbalance creates an electric dipole. When the attraction between dipoles and adjacent molecules causes them to interact, they form weak bonds between the molecules. Hydrochloric acid, HC1, is an example of a polar molecule where the molecules are held together by permanent dipole-dipole forces. Temporary induced dipoles. All atoms and molecules have electron clouds. Within a bond of the electron are a constant motion and oscillate. For brief nanoseconds, electrons may be clustered more to one side, creating a charge that quickly disappears. The temporary negative charge will attract a temporary positive charge from a nearby molecule, a process called the London dispersion force of attraction. For example, the interaction between iodine molecules is a temporary dipole bond. The London dispersion force is the weakest of the secondary bonds. It is responsible for the condensation of nonpolar atoms or molecules into liquids or solids with a drop in temperature. The 3 states of matter. Matter exists in 3 states or phases: solid, liquid, and gases. Solids have the strongest attraction between atoms, and molecules have both shape and volume. A liquid has volume but no definite shape, and a gas has neither definite shape nor volume. Most materials are mixtures of more than one state of matter. For example, plaster is a mixture of both solid and liquid, and fluoride foams are a mixture of a liquid and a gas or air under pressure. Gases are used mostly as propellants in dispersing or mixing dental materials. Therefore, this chapter will limit the discussion to the general properties common to solids and liquids. Solids. In solids, the atoms are packed tightly together, and this restricts their movement, providing them with a fixed shape. Primary bonds hold the atoms of solids together, giving them strength and stability. Solids maintain their shape and resist forces that try to deform them. Solids are found in 2 main forms, crystalline or amorphous. Crystalline solids have an ordered, 3-dimensional symmetrical pattern or lattice network that repeats throughout the crystal. There are 14 different types of lattice structures. Many materials, such as table salt, are crystalline solids. Because of their structure, crystalline solids cannot be compressed into smaller shapes. Within the lattice structure, all bonds between particles are equal so that when heat is applied, all the bonds are broken at the same time, producing a definite melting point. Ice transforms from a solid state to a liquid state at a melting point of 0 degrees Celsius at standard atmospheric pressure. Non-crystalline solids called amorphous solids have atoms in non-repeating arrangements similar to liquids. They do not have a definitive melting point but soften gradually as heat is applied. Examples of amorphous solids include many dental waxes and glass-type ceramics. Liquids. Unlike the molecules of solid, molecules in a liquid state are not confined to patterns. Therefore, liquids can easily change shape and can flow. So the study of this flow is the science of rheology. Fluid flow can be steady or unsteady, and flow has a major influence on the handling and delivering of dental materials. For example, impression materials that are placed around the prepared tooth must flow readily to capture the fine detail of the preparation, while impression materials that are placed in the impression tray should exhibit less flow. The movement of a liquid would depend on the characteristic of the liquid and the surface at which it is placed. Viscosity is the resistance of a liquid to flow. Values of viscosity depend on the nature of the fluid. Thin liquids have low viscosity and thicker liquids have high viscosity. Water flows readily and therefore has very low viscosity, whereas higher viscosity liquids, tree sap for example, have greater ability to resist flow. The viscosity of liquids usually decreases as temperature increases. Some viscous liquids will flow more readily under stress, a property called thixotropy. For example, when they are mixed, shaken, stirred, or manipulated. Fluoride gels are often advertised as thixotropic. This gives the operator control of the gel while it is delivered in the tray so that it does not drip out when inserted into the patient's mouth. Once the material is in the mouth, however, the patient is instructed to chew on the tray, decreasing the material's viscosity and allowing its flow into pits and fissures and interproximally to improve penetration into all surfaces. Gypsum products, when mixed with water, are a slurry, a watery mixture that can be poured into an impression to create a solid cast when it hardens. Some materials, like waxes, appear solid but are really super cooled liquids. They can be caused to flow under loading forces or can deform under light stresses. Liquids, when heated, eventually vaporize or boil. Water transforms from a liquid state to a gas state, steam, at its boiling point of 100 degrees Celsius at standard atmospheric pressure. The lower the atmospheric pressure, the lower will the boiling point be. Next, properties of dental materials. Properties of dental materials are of 3 basic types: physical, mechanical, and chemical or electrochemical. Physical properties are those properties that can be observed and measured without changing the composition of the material. Physical properties include such things as melting and boiling points, density, viscosity, thermal conductivity, and thermal expansion. Density is a measure of the weight a material has compared with its volume. It is a measure of the compactness of matter, or how much mass is squeezed into a given space. A brick and a sponge of the same dimensions have the same volume, but the brick is much denser. The sponge has many large air spaces throughout. If you squeeze the sponge, the volume and the air spaces are reduced and the sponge becomes denser. Less spacing is seen between the atoms. The close spacing of the crystalline structure gives the greatest density. Enamel is the densest of the tooth structures, and gold is the densest of the restorative materials. Mechanical properties are a subset of physical properties. They are physical properties that are seen when a load of force is applied to a material. They include such properties as hardness, stress, strain, fatigue, strength, elasticity, stiffness, resilience, toughness, ductility, malleability, and durability. Hardness is the resistance of a solid to penetration. Hardness is also used to define a material's resistance to wear and abrasion. The hardness of a dental structure or material determines the extent to which it is scratched by an abrasive material. Enamel and porcelain, 2 of the hardest materials, are more resistant to being scratched than are cement and dentin, or composite resins and gold crowns. For this reason, it is very important that the type of restorative material or tooth surface be determined first, before beginning the procedures with abrasive agents. Hardness test. There are several tests designed to measure the hardness of materials, and they all measure the material's resistance to being indented. KNOOP, K-N-O-O-P. hardness. NUP hardness is the value usually given for dental materials. The testing head is shaped like a pyramid for the NUP and Vickers test, a cone for the Rockwell test, and a ball for the Brenner test. The NUP test uses lower pressure for pressing the diamond head into a material than the Vickers test, so it can be used to test a variety of materials, including thin or brittle materials, such as ceramics. The size of the indentation is measured and the hardness is calculated based upon the size. The smaller the indentation, the harder the material is. The Vickers test is used mostly for testing metals. Stress develops within a material when a force is applied. The larger the area over which a force is distributed, the less will be the stress. Stress can occur singularly or in various combinations depending on the direction of the applied force. When a solid is subject to an external force of sufficient magnitude, it undergoes change in size and shape and is considered strained. The amount of stress placed on a material at the time it breaks is known as ultimate strength. A material does not necessarily have to break when subjected to external compressive, shearing, or tensile force. It may deform. If this deformation is not permanent and the material recovers from the force completely, it has good elasticity and has undergone elastic deformation. A rubber band is an example of a material with elasticity. Plastic deformation, on the other hand, occurs when a force or stress produces an irreversible change in a solid material's shape or size. Not all materials return to their original shape when the deforming force is removed. Materials that do not return to their original shape have exceeded their elastic limit and start to permanently or plastically deform. The stress at which plastic deformation begins is called the yield stress. Rubber can be deformed quite a bit before permanent deformation occurs. Elasticity is important for impression materials, which must be stretched over the tooth or bony undercuts without permanent deformation. Elasticity is important for orthodontics, where wires and springs are deformed and the force they generate in returning to their original shape moves the teeth. These wires do not recover immediately. Rather, they recover over a period of time and with some degree of permanent deformation. This slow progressive recovery is important in the controlled movement of teeth. The relationship between stress and strain is useful for comparing properties of materials so the best material can be selected for a given application. The relationship can be plotted on a graph with values of stress on the vertical axis and values of strain on the horizontal axis. The resultant curve plotted on the graph represents the behavior of materials when subjected to load. It provides useful information about the strength and the ductility of the materials and can compare the response of different materials to the same load. The stress-strain curve for each material is unique, but it is possible to find some characteristics in common among various groups of materials. For example, stress-strain curves for brittle materials or ductile materials have similar characteristics. The stress-strain curve for brittle materials, such as porcelain, has only an elastic region followed by a fracture of the material. There is no yield point, and the ultimate strength and the fracture strength are the same. Young's modulus measures the resistance of a material to be deformed. The stiffness of a material, the lack of elasticity, means that it resists being deformed and is measured by Young's modulus, also called elastic modulus. Stiffer materials have a higher modulus. Enamel has a high modulus. Restorative materials should have a modulus that is compatible with tooth structure. We usually do not want dental restorations to bend or compress when a force is applied, so materials such as amalgam, composite resin, and ceramics should be stiff. Resilience is the amount of energy a material can absorb without permanent deformation. Impression materials and orthodontics wires must be resilient to be successful. When impression is removed from the patient's mouth, it needs to deform to be slipped over the contours of the oral structures. To be an accurate impression, it is equally important that the material returns completely to the original shape of the oral structures impressed. Toughness is the ability of the material to absorb energy without fracture. Restorative materials must exhibit toughness. Brittle materials have limited toughness because small amounts of deformation will cause fracture. Traditional porcelain restorations are much more likely to fail on the occlusal surface of posterior teeth than gold restorations. Newer ceramic materials, such as zirconia, are very tough. Pulling or stretching of the orthodontic wire under tensile stress is a measure of its ductility. That is the amount of dimensional change it can withstand without breaking. Gold is very ductile. Gold is very ductile since it can be elongated close to 20%. Materials with poor ductility are classified as brittle. These materials are much weaker than when subjected to tensile forces than to compressive forces. Porcelain is brittle and cannot undergo much tensile stress without fracture. Its ultimate strength is about equal to elastic limit. Gold is not only ductile, but it is malleable too. Malleability means that it responds easily to compressive stress and can be hammered into thin sheets without fracture. The combination of malleability and ductility gives this metal the ability to resist fracture even at fine margins, giving gold edge strength. These characteristics allow for the superior edge strength of gold crowns. Amalgam does not have good edge strength. If an insufficient amount of amalgam is present at the edge of a restoration, the forces of mastication will likely cause fracture of the material at the margins. In most cases, noble metals tend to be ductile and malleable, but ceramics are brittle. Ceramics and composites are described as brittle because they will sustain little strain before they fracture. Fatigue. Fatigue occurs within a material when it is subjected to repeated stresses and can result in a sudden failure or fracture of the material. Microscopic flaws or cracks develop within the material that progress with repeated loading. This can be seen when a strip of metal is bent back and forth repeatedly until it breaks. Likewise, weak cusps of a tooth may fracture over time from repeated chewing forces placed on them. Durability refers to the ability of a material to withstand damage due to pressure or wear. Both porcelain and metal are very durable, resilient, and tough, and can absorb stress without breaking. Porcelain is brittle, however, and cannot withstand shearing stresses as well as metals. Metals are very durable, but not as aesthetic as porcelain. All ceramic crowns have replaced porcelain in many applications and provide excellent mechanical properties, as well as aesthetics. Amalgam is durable and provides longevity and cost-effective alternative. Amalgam restorations lack aesthetic and contain mercury, which some offices have chosen to eliminate from their environment. Composites provide a durable option in areas where aesthetics are important, but they can stain and do not resist abrasion as well as other restorative choices. The new nano-composite materials have improved this restorative choice. To adequately evaluate the best restorative choice, durability and aesthetics are both important. Chemical properties. Chemical properties are those that involve a chemical reaction that changes the material into one or more different materials. Atoms that have rearranged and a new material is formed. Some of the chemical reactions in the mouth involve an electrical current, and these are called electrochemical reactions. Corrosion is the most common electrochemical property seen in the oral cavity and seen as most often with metals. A very common form of corrosion seen in your neighborhood is a rusting iron gate, nail, or other iron object. Oxygen in the air oxidizes the iron and forms iron oxide, otherwise known as rust. The iron has been chemically changed. Galvanism is an electrochemical reaction that occurs when two dissimilar metals contact each other in the presence of solution containing electrolytes such as saliva. It acts like a battery and produces an electric current, causing the patient to experience electric shocks and or a metallic taste. Classification of materials. Restorative dental materials can be classified by their composition and divided into categories of metals and their alloys, ceramics, and polymers. Metals have properties such as strength, ability to conduct electricity and heat, malleability, ductility, and luster. Metals and their alloys are used for amalgam restorations, implants, partial dental frameworks, and crowns and bridges. Ceramics are strong but generally are rigid and brittle and melt at high temperatures. They are poor conductors of heat and electricity. Ceramics are popular for aesthetics, crowns, and veneers. Polymers can occur in long chains that give certain properties depending on how the chains are linked to each other. Some polymers can be flexible, easily shaped, and rubbery, while others can be hard, rigid, and difficult to mold into shapes. They can be used for denture bases and denture teeth, for example. Composite resins are combinations of polymers and ceramics. The polymer component allows the material to adapt to the walls of the cavity preparation and be shaped, while the ceramic component adds wear resistance and provides color and other optical properties for aesthetics. Materials can also be classified by their application, how they will be used and fabricated, and their expected longevity. They may be preventive, therapeutic, or restorative. Preventive materials are directed toward preventing the occurrence of oral disease, trauma to teeth and jaws, and promoting oral health. Fluorides, pit and fissure sealants, and polyethylene materials for sports guards are preventative materials. Therapeutic materials are used in the treatment of disease and include materials such as medicated bases or topical treatments for periodontal disease. Restorative materials represent the largest classification. This classification applies to any filling, inlay, crown, bridge, implant, or partial or complete denture that restores or replaces lost tooth structure, tooth, or oral tissue. Restorative materials may be used for short-term, temporary crown cements, or for long-term, permanent restorations, prosthetic implants, or orthodontic appliances. Restorations may be further classified as direct restorative materials or indirect restorative materials. Direct restorative materials are fabricated directly in the mouth, whereas indirect restorative materials are fabricated outside the mouth, often in a dental laboratory, using replicas of the patient's dentition and then placed in the patient's mouth. Some materials, such as amalgams and composites, may be fabricated directly in the mouth. Other materials, because of convenience or toxicity or other physically harmful characteristics, need to be fabricated indirectly outside the mouth and then placed into the oral cavity. Porcelain, for instance, needs to be fired to temperatures higher than 1,000 degrees Fahrenheit, making indirect fabrication necessary. Materials are classified by longevity, that is, how long they are expected to hold up in the oral cavity. Although all materials will degrade, wear, or fracture over time, permanent restorations are expected to be a long-lasting replacement for missing, damaged, or discolored teeth. Temporary restorations, also called provisional restorations, are used for short periods of time, several days to weeks. They function in the place of the permanent restoration to protect the teeth, prevent sensitivity and unwanted tooth movement, maintain the health and the contours of the periodontal tissues, enable the patient to function normally, and provide temporary aesthetics in the prepared area. Intermediate restorations, like provisional restorations, are placed for a limited time. However, the time they may extend from several weeks to months. These restorations are not expected to replace tooth structure permanently and are generally used when there is other ongoing treatment, such as orthodontics or implant therapy, that is needed before a permanent restoration is required. Composition. Materials may be classified by their composition. Components and their reactions of those components may aid classification of materials. Many types of dental materials require the combination of two components to form the resulting final material. These initial two components may begin as water or powder, liquid and powder, paste and liquid, paste and paste, paste and initiator, the blue light. Dental plasters begins with water and powder components. Composite restorations may require a paste with a blue light as an initiator. Many of these components are classified as catalyst and base. The catalyst is responsible for the speed at which the reaction occurs and is often the liquid component. Components may be measured and dispensed as catalyst and base or packaged in predisposed amounts. Reaction activated by mixing. When components are mixed together, a reaction occurs. This reaction may be physical, involving the evaporation or cooling of liquid, or it may be chemical, creating new primary bonds. Most reactions of the two components result in a solid structure. Before the material reaches its ultimate solid state, the process goes through stages, the manipulation stage and the reaction stage. Both stages are defined in units of time. The manipulation stage includes the mixing and working time, and the reaction stage includes the initial set and the final set time. Mixing time is the length of time the dental auxiliary has to bring the components together into a homogeneous mix. To allow the clinician the full working time, mixing times must be strictly observed. The working time is the time from the mixing the material until it begins to harden and is no longer workable because it has reached its initial set. The initial set time coincides with the end of the working time, and it occurs when the material no longer can be manipulated in the mouth. The final set time is that time needed for the reaction that begins when the material is mixed to go to completion and the material hardens in its permanent state. Mixing and working times often offer some control variables. Mixing slowly and cooling the components can increase the working time. The addition of more catalyst may decrease the working time. Control of these variables is important for some situations. For instance, when working with pediatric patients or patients who have a limited opening, decreasing the working time may be desirable. When one is working with a large amount of restorative material, an increase in working time may be required so that the material can be manipulated for a longer time. The amount of working time also may be controlled by how the reaction stage is initiated. There is chemical set materials, light activated materials, and dual set materials. Chemical set materials are those that set through the timed chemical reaction of a catalyst and base. Once the two components come in contact with each other, the chemical reaction begins and continues through the reaction stage. The clinician has little or no control of the time except cooling the material before mixing. For this reason, many clinicians have selected a light-activated system for their materials. Light-activated materials use a light source in the blue light range to initiate the reaction stage. Both components are present in the material but do not react until the material comes in contact with the blue light source, thus giving the clinician unlimited working time. Dual-set composites have a slow chemical set that is activated when components are mixed, but the set can be accelerated by light curing. This gives the clinician much more control of the working time and gives assurance of complete setting in a deeper or more difficult-to-access area of the mouth or preparation. The setting times, initial and final, are important to the auxiliary as well as the clinician. The materials must not be disturbed after the initial set has occurred. Moisture and pressure controls are frequently important during the initial set. Moisture contamination from saliva or blood during the initial set time may have an adverse effect on many dental materials, causing them to fail. Continued firm pressure from biting force or from holding the material firmly in the mouth is essentially for materials needed intimate contact with the tooth, such as dental cement. The final set of the material may occur while the patient is still in the office or several hours later. Many amalgam restorations meet their final set 8 hours or more after placement. Appropriate patient postoperative instructions on when and what to eat, what to avoid, and how to place pressure on the restoration are essential to avoid fracture of these materials. The accompanying box gives an example of manipulation instructions on dental cements, including units of time. Variables in the manipulation of materials begin with the ratio of the components. Manipulation of materials. Manipulation of materials components is an important consideration for the dental auxiliary. It is through this manipulation that the final characteristics of the material are achieved. Some materials offer some variations in their manipulation. Others are very technique sensitive, and even the slightest variation will have a detrimental effect on the final product. Variables in the manipulation of the material begin with the ratios of components. The manufacturer, using the weight and volume of the component, recommended specific ratios. Many materials are produced as separate components that need to be measured and dispensed according to the manufacturer's recommendation. Manufacturers also produce materials in pre-measured units, eliminating the need to measure and dispense the components, thus standardizing the ratios. Changing the ratios of the materials by adding more catalysts may result in a faster reaction. Increasing the amount of water or liquid component may also result in less dense, weaker material. These ratio changes are variables that permit the clinician to alter manipulation and reaction time for some materials but are contraindicated with other materials because of the adverse effects. Manufacturers give directions as to when variation is needed and how much variation in ratio materials can withstand without adverse results. The auxiliary is most often responsible for measuring and dispensing the components. Strict adherence of ratios is required for some materials, whereas others allow more flexibility. Effects of temperature and humidity. External variables such as the temperature of the material and the room temperature and humidity can also play an important part in the manipulation of materials. In general, high temperatures and humidity will accelerate the reaction of the material's components, and low temperatures and humidity will retard the reaction. Mixing of components. How the components of the materials are mixed, that is, quickly or slowly, on a pad of paper, glass slab, or by hand mixing or using automatic mix dispensers. Those all will affect the final material and its consistency. Materials mixed slowly on a cool glass slab will usually produce a slower reaction. Auto-mixed materials will give a more consistent result because the materials are mixed by equipment in a standardized manner with controlled proportions, eliminating the variables of human error. Shelf life. The shelf life of a material refers to the length of the time a material can be stored before it becomes unsuitable for the use. The shelf life varies from material to material and will be impacted by how it is stored. Temperature extremes and high humidity should be avoided. Plaster and other gypsum products will begin to deteriorate if exposed to high humidity. Materials should be stored in sealed containers. Some materials require refrigeration to prolong their useful life, and others need to be protected from direct light and may be packaged in light-blocking containers. Always refer to manufacturer's directions to determine conditions of storage and expiration. Check with the dental supplier to see what the materials are shipped under conditions that will not adversely affect the shelf life, such as seasonal temperature variations. The expiration date for all materials stored in the office should be monitored carefully. Materials should be organized such that the older materials are used before new shipments prevent them from expiring. Many materials will lose their potency or fail to set properly if they have passed their expiration date. While some materials may be able to be used a few months beyond their expiration date, it is risky to use them because they may lack their optimum performance and the treatment they were used with may fail. The American Dental Association requires materials that meet its specifications to stamp a date of production on the packaging of the material. The summary. The physical structure of a material helps to define the characteristics expected from the material. The success of dental materials is directly related to the choices the dental auxiliary makes in selecting and manipulating the components while keeping in mind those variables that cannot be altered. Controlling variables of a manipulation reaction stages has become increasingly important with more sophisticated materials and more challenging clinical situations. Hand mixing of materials allows for some control of manipulation in reaction stages. However, inconsistencies in mixing and time demands have become problematic in many clinical situations. Manufacturers are producing materials in a variety of forms to address these concerns. Pre-measured materials are manufactured to standardize the amount of catalyst and base included in the mix, thus preventing inconsistencies in resultant physical properties. Auto-mix materials standardize the amount of catalyst and base and produce a consistent, homogeneous mix. It is important to refer to manufacturer's directions for instructions on storage, proportioning, and mixing, and on variables that may be altered to produce the best final results for a given clinical scenario.